Yes, hello, this is Tom Smith. Welcome to our monthly Small Systems webinar series. Today's topic is high rate wastewater treatment for peak wet weather flows. We are pleased to offer continuing education contact hours for this webinar. To get such, you need to be registered for this, and on the screen you can see where you can go to register. Also, the requirements for the contact hours. Excuse me. The requirements for the contact hours are that you need to be registered or be in a room with someone who's registered.
Not logged in must be provided
by the person who is logged in. So, and you can do that to the website indicated below. Unfortunately, you cannot get certificates for viewing this webinar after this live presentation, and so you can only get it for the presentation for this next hour. So today we're very pleased to have two excellent speakers, Kevin Weiss and Daniel Murray, speaking on this issue. We'll start with Kevin, followed by Daniel. We will not have questions until after the second speaker. However, during the course of the webinar, please, if you have a question, feel free to put it in the questions box in the GoToMeeting dialog box on your screen. We'll be able then to sort those and then ask the speakers the questions at the end of both presentations. So to start, we'll start with Kevin Weiss. Kevin is a chemical engineering with the Office of Wastewater Management in the Water Permits Division. He joined the division in 1987, where he worked on municipal wet weather issues and integrated planning. During this time, he worked on stormwater regulations, the Phase 1, draft SSO, CMOM regulations, blending policies, the integrated planning framework, and the November 2014 Financial Capability Assessment Framework. Kevin holds a Master of Science in Chemical Engineering from Carnegie Mellon and a JD from the George Washington University in Washington, D.C. So with that, I will give the floor to Kevin.
Thanks, Tom, and thanks to the audience. Today I'm going to be talking about wet weather problems down at wastewater treatment plants, and in particular with blending that occurs at those plants. And let me start with a problem statement, if you will. Wet weather issues have really come to the limelight in the NPDES program, and they pose specific problems for treatment plant operators. About 770 communities have combined sewers which feed into wastewater treatment plants. And during wet weather, the flows from these collection systems, as well as from some leaky sanitary sewer collection system, can dramatically increase the flows to the system. These intermittent high flows can cause significant problems at the wastewater treatment plants. In particular, for treatment plants with activated sludge units or with BNR units, the biological treatment unit can be the most vulnerable process at the plant. High flows can wash out the biomass, or dilute flows can lower the activity of the biomass and therefore lessen the treatment efficiency. Traditional management approaches have been to limit the flows entering the treatment plant and send untreated sewage out through combined sewer overflows. And more recently, municipalities have been asked to minimize their CSOs and to maximize their flows to the treatment plant. A number of municipalities, including Washington, D.C. and Cincinnati, are working on tunnel systems to collect large amounts of wet weather flows from that would otherwise be CSO discharges. But when they go to empty these out, these result in large volumes of flow being sent to the treatment plant. And in addition, many treatment plants are installing BNR systems that are more sensitive to high flow. So this is really becoming a big issue for the agency, these wet weather flows. And with that, what I'll be talking about is a blending scenario. when treatment plants can't discharge out an overflow point, the flow gets down to the treatment plant, what they can sometimes do is provide primary clarification for the flows, all the flows coming into the plant, and limit the amount of flows going through biological treatment by bypassing the flows around the biological treatment works. I'll use the term blending to describe the scenario where flows are mixed back with treated flows from the biological treatment system prior to disinfection. The other scenario I'll be looking at is when a wet weather treatment unit, typically a non-biological system, is put on the diverted flows prior to blending. We've been looking at this issue for a couple of years now, and in 2014 we invited a number of engineering and public health experts to discuss some of the implications with blended discharges. We ended up with 7 public health experts and 5 engineering experts. An in-depth summary of the forum that we had is on our website. We started the forum with a discussion from our engineering experts, and some of the key points that they raised is that we had to be aware that performance of our treatment plants are degrading during wet weather, and that it wasn't always possible to reduce the peak flows to a point where the biological system wouldn't experience difficulties. There are some things that could be done at the plant to reconfigure the flows through the biological treatment unit, but at some point that started to decrease the treatment effectiveness. And the experts said that, one thing that we should be looking at are physical chemical methods to treat the wet weather flows. And they emphasized that there's going to be more and more problems with wet weather flows as more nutrient controls get online at treatment plants, and they're again being more sensitive to these wet weather flows. The public health experts had talked on a number of subjects which are listed here. The first being the knowledge gap, and one thing that they emphasized that the human health risks associated with wet weather flows and blending in particular at treatment plants is going to be very site specific, that we weren't going to have EPA studies to guide us through what the specific health risks were, but what we would tend to have to do is to look at monitoring data from specific facilities and take a look at the receiving water and make estimates on the impacts. One major problem facing us is that most facilities take a look at bacteria indicators and that those are very limited in ways that I'll discuss later on. The biggest limitation is associated with the lack of correlations with viruses. A lot of studies have shown that viruses are really the leading cause of illnesses associated with recreation water contact. And that the bacteria indicators that we're tending to use now are not good indicators of assessing the risk of viruses. So this was going to be a big issue for us. The engineers stressed the importance of the disinfection unit. They indicated this is probably the most important unit for reducing viruses and other pathogens. And really, the way a lot of the engineers looked at it was that they start with the disinfection unit and use that as the basis for plant design. However, the engineers recommended that there were cases where side stream treatment or physical chemical treatment on flows diverted around the secondary treatment units would be appropriate and would be something we really should take a look at. And they felt that a well-designed physical chemical unit could give us performance that was comparable or better than the traditional biological units working under stressed conditions. The importance here is to remove the solid so that that will improve disinfection. With some of the gaps that we noted coming from the public health forum, we realized that it was important for EPA to try to gather data on the performance of treatment plants under wet weather conditions, and that led us to develop to work on our current project, which is the development of a blending compendium, which will try to summarize data from facilities around the country. We're working with WEF and other stakeholders to try to gather data on this, and this is an ongoing project. I want to set the stage for the compendium a little bit, and looking at everything that's going on during wet weather, there's a lot that needs to be done in terms of reducing the peak flows and the loading. Unfortunately, the compendium's not going to do that. We're just going to focus on the treatment plant, and we're going to look at ways that are being done to increase biological treatment capacity as well as improve primary treatment and to look at treatment of diverted flows. We're hoping to present some data on facilities that blend. Unfortunately, we haven't been able to track down a lot of data that specifically looks at blending at facilities. So what we are also going to do is look at the performance of some of these physical chemical treatment systems. We have two major studies that took a look at blending without any sort of side stream treatment. The first was a WERF study that looked at the East Bay Mud facility, which is located in Oakland, California. And this was a system that was serving a sanitary sewer system, so the flows were high, but they weren't tremendously high, and it also had a very good disinfection process going on. So in this particular case, we did see some slight increases in some of the pathogens for when blending was occurring, but really the data was very comparable to what was happening without blending during wet weather, or even with what was happening during dry weather. We had a second study that ORD helped develop in working with the IEC, and there they were looking at three treatment facilities in New York City that were served by combined sewers. Now, because these facilities were served by combined sewers, they were having a lot higher flow conditions. Also, we had noted that there were some operational problems at some of the facilities. And this all goes to point that the data that we tend to look at from wet weather facilities is very site-specific. One of the keys, I think, in this particular study was the disinfection units. And here they had limited capacity in their disinfection units, and when they got into a wet weather scenario, they had to cut down the contact time for the chlorination that they were using. And as the data showed in the previous slide, there was much less pathogen reduction during blending. Another part of their study was to look at the particles in the effluent. And what they did was they took effluent samples and put them in a blender and then retested the samples coming out of the blender. And what they were finding was that the effluent did have a significant amount of particles in it, and when it went through, the particles went through the disinfection process, the pathogens on the outside of the particles were killed. but they remained viable inside the particle. And when they got into this blending environment, they were released, and hence you had much higher counts of pathogens after they were blended. So we've been looking at facilities that try to do different techniques to improve the treatment at the plant. One of the things we've been looking at is chemically enhanced primary treatment. And here you can see that we have some fairly significant improvement in terms of TSS removal, which is ultimately going to help us with our disinfection. In addition, we are able to increase the capacity of these primary treatment units by using chemicals to enhance the treatment. We were also able to look at a number of physical chemical treatment systems on the diverted flows around the biological system. One was a ballasted flocculation system. The vendor refers to, or the trade name is ActiFlow. And in terms of blended effluent, we were able to identify 2 facilities that had good blending data, and we tend to focus a lot on the BOD and TSS data. And as you can see, you're getting good TSS removals during blending, particularly for the Lawrence facility, somewhat of a reduction for the BOD, particularly in the Wisconsin facility. In addition to the blending data, we also had some specific data on how the unit itself was performing. So this was coming straight from the unit without blending. And I think one of the things that this really shows is that the performance of these facilities really depends on the how well the system's operated and sort of what sort of chemicals are used in terms of preparing the solution for the ballasted flocculation system. And you see a fair amount of variance here. The Lawrence facility was sort of our star facility, and we talked a number of times to the operator of that, and he just attributes it to 10 years of experience in running it, and that they really emphasize training their personnel and trying to really fine-tune what's going on with it. And the results show here. Some of the other facilities are not getting as good results. The vendor for the ActiFlow facility made some modifications to this facility to try to get some additional BOD removal. And they added a biological component to it with a short contact time on the order of a minute or so. But that short contact time was able to get significant results in CBOD loading reductions. And here, depending on how the system is run, they were able to get above 90% removal for CBOD. And what our enforcement folks found when they took a look at that system was that that system, as run under those conditions, was able to meet our secondary treatment regulation requirements, which is a big deal for the in the wet weather context. We also looked at the Densideg product, which is another form of ballasted flocculation. We're getting data from a facility in Toledo. It's a 185 MGD facility, and it's come online a little bit more recently, so we're interested to see what the trends will be with performance on this. Some of the other types of technologies we looked at were compressed media filter. In Springfield, Ohio, just installed a fairly large facility, and we're taking a look at some of the data there. Another type of technology that's been developed more recently is cloth media filtration, and we have one pilot study using this optofiber system, which uses microfibers, and when they're using alum, they're getting quite good removals, over 90% for BOD and 96% for TSS. Our study, we were able to also get data on various techniques for increasing the biological treatment capacity. We looked at step feed increases, where a facility was able to increase the biological treatment capacity by around 40% before the treatment efficiency started to drop off notably. And we also looked at the biomag system, which is a ballasted flocculation system which used magnetic particles to increase the settling. And there we were able to find facilities were able to increase their capacity by a factor of 2 to 4, which is, again, a very promising technology for us. And I think that will wrap up my end of things. I'll turn it over to Dan and look forward to questions after he's done. Thank you very much.
Duties is that, again, if you have any questions for either of the speakers, please put them in the question box in the GoToMeeting dialog box on your screen, and we'll sort them and answer them after Dan Murray's presentation. Also, if you missed the original poll in terms of how many people are in your room, you can put that in the question box also for us, and that helps us document the importance of this webinar series. So, our second speaker today is Daniel Murray. Dan is a senior environmental engineer with the Office of Research and Development in the Water Supply Water Resources Division. He began his career in EPA in 1977, where he worked in Regions 1 and 5. In 1987, he left EPA to work at the Massachusetts Water Resources Authority, where he led the authority's combined sewer overflow control program. But back in 1990, he returned back to the EPA and joined the Office of Research Development in Cincinnati, Ohio. In 1995, he received the Gold Medal for Exceptional Service in support of the development of the agency's CSO policy. He implemented EPA's Aging Water Infrastructure Research Program, among other things. So Dan holds a Master's of Science in Civil Environmental Engineering from the Northeastern University in Boston, and he's a registered professional engineer and board-certified environmental engineer. And with that, I'll give the floor to Dan.
Thanks a lot, Tom. As my title slide says, what I'm going to do is talk about an evaluation we did on a high-rate wastewater treatment plant here in Cincinnati, and I'll move forward to, first of all, I want to thank Kevin for his, I think a lot of the things you'll hear from me will dovetail quite well into a lot of the comments Kevin made, and I think having worked with Kevin for a long time, I think you know, he's really tied into the regulatory side, and some of the findings of this evaluation will fit in and reinforce some of the statements he made here just a few minutes ago. Very quickly, I'll provide a shortened background because Kevin did a real good job, so I won't waste a whole lot of time doing that. The technology that we looked at here in Cincinnati is the ActiFlow ballasted flocculation technology, and I'll quickly show a schematic of that technology, and then a little more detail into that technology as it is laid out here in Cincinnati at the Metropolitan Sewer District's SSO 700 facility. Show the process flow, talk in general the operational goals of the plant, define and explain the sampling program that we conducted at the facility, discuss some results, and then end with a summary and a couple summary and conclusion slides. Again, I won't repeat this because this is pretty much verbatim what Kevin said. So I'll just repeat that urban wet weather flows are a challenge to our utilities in this country, both as they affect overflows, be they CSOs or SSOs, and obviously threaten biological treatment at either secondary or biological nutrient removal facilities. As a result, many utilities are increasingly employing high-rate treatment systems to either treat overflows or to manage those flows in excess of design flows for biological treatment at POTWs. This project will focus on is the evaluation of a dialysis flocculation and UV disinfection system, treating wet weather flows from a separate sanitary interceptor here in Cincinnati at the Metropolitan Sewer District, commonly referred to as SSO 700, because the plant is upstream of a known SSO, and the main purpose is to offload flow from that interceptor to eliminate that overflow. During the time span of January of 2013 and May of 14, we conducted 15 wet weather sampling events to conduct our evaluation. As I said, this is a fairly simple depiction of the active flow dialysis flocculation process. If you look here in the lower left, the black arrow, that's the influent coming into the facility. It enters a flash mixing zone where chemicals, typically coagulants and polymers, are added in succession, and the ballasted part of the equation in this technology is a microsand that is also added to this this high flash mixing zone. Now that can be either as a recycled sand, and I'll explain that here in a second, or there is some loss of sand with the sludge, and occasionally additional sand has to be added to make up for the amount needed to operate the plant appropriately. The flow then moves into a more gentle, slow mixing zone for flocculation, for floc development, and then it flows into a settling basin, and the design is an upflow settling basin with lamellar plate separators to enhance the settling of the ballasted floc. Then the clarified effluent proceeds out of the technology, typically going on a disinfection, or maybe moving into advanced treatment at a POTW, for example. But what I want to touch on quickly here is that the sludge is removed from the bottom of the settling basin, and the sludge sand mixture goes to a set of hydrocyclones where the sand and the sludge is separated, and that's up around the number 12 there in the upper left part of the diagram. And again, that sand is returned to the facility, to the plant, and then the sludge is removed for processing. So what I want to do is with that in mind, talk about the facility here in Cincinnati. And it's really made up of three major components. The first being the influent pump station, where we have the interceptor comes through the pump station. It's a 42-inch interceptor that comes into the pump station, and at certain elevations of flow during wet weather, that flow falls into the wet well, and one of four one or more of 4 pumps pumps the water into the 3 storage tanks in the lower right. The influent pump station is equipped with 4 10 MGD submersible pumps. Any one time, 3 of those pumps could be operating for a maximum capacity of 30 MGD. One pump has a VFD for lower flows below 10. The pump station can pump to tank number 1, tank number 2, or directly to the high rate treatment facility. Here are the 3 storage tanks. As I said, typically how the plant operates is as flow comes in and pumping begins, the first volume of flow goes to tank number 1. Tank number 1 is filled, and flow then proceeds to tank number 2. The flow that moves to tank number 1 is held, and when the storm passes, is returned to the interceptor for full treatment at the wastewater treatment plant. Now, the reason behind this is if there's a first flush load in the flow coming into the facility, it's captured in that first 1.2 million gallon tank and held. Then, as I said, if flow continues, it goes into number 2 and then overflows into number 3. As I said, there are 3 1.2 million gallon tanks. The ability to store and release to the interceptor for treatment, or the ability to release to the high rate treatment facility. Now, during extreme events, the flows can and may overflow and discharge to the receiving stream, mixed with the effluent from the high rate treatment plant. Now, that high rate treatment plant here is the active flow plant combined with, or the ballasted flocculation plant combined with UV disinfection. We have a high rate treatment facility and the active flow plant with a range of 3 to 15 million gallon capacity, and you can see there how that translates into hydraulic detention time. And the addition of chemical coagulants, polyaluminum chloride, polymer, and microsand, all added to the high rate treatment facility for ballasted flocculation. Downstream of that facility is the UV disinfection facility, which has a capacity of up to 15 MGD. Okay, what I want to do here is get a little more specific to the exact facility in Cincinnati and show quickly how the flow moves through the facility and how the process adds the chemicals and sand, moves through the settling tank, and moves towards the disinfection. So you can see the upper left here is the flow coming out of, there's a fine screen that happens. The flow comes from typically tank number 2 and comes into the facility, goes through a fine screen, and enters this first chamber here, where it moves around a wall, and the first chemical is added, and that's the coagulant, and it's added through the chemical induction unit, which is, I kind of think of it as it's a small blender where that, rather than, it isn't just dripped in, it's added and mixed actively to disperse that coagulant in the flow, prior to then coming up and flowing over the wall between that chamber and the injection tank, or the high mix tank, where the polymer is added, and the high-speed mixer mixes those two chemicals together, and just as importantly, resuspends or suspends that microsand. It's a very fine sand, and that high rate mixing mixes that sand so that it is available to then react or coagulate or flocculate with the other two chemicals. I mentioned the sand. In addition to that sand comes in from the settling tank sludge draw-off, goes to the hydrocyclones, and the lighter color arrow is the recycled sand returning to that injection tank, and the darker arrow is the sludge that would be sent to the interceptor and down to the treatment plant. So that mixture is then underflows into the flocculation tank. That, again, a very low speed mixing to enable that that floc to form and overflow into the settling tank. It underflows a baffle and then comes up through the lamella plate settlers and moves towards to the disinfection system on the right. And here's the other half of the facility. That flow from the settling tank comes in, goes through the two cells of UV lamps and out into the Mill Creek. Now that flow can also be diverted to the wet well in the influent pump station. In fact, that's what happens for the first 15 minutes or so as the plant is started up and things are brought to operational levels in terms of the operation and the so that full, and then the flows are increased to operational flows as well. Overall, the plant has, I've characterized three major goals, and the first goal is to maximize storage. In some cases, when a storm is fairly small and the flow into the plant doesn't exceed the storage capacity of the plant, then the goal would be to maximize that storage, hold that flow, whether it's tank 1 and whatever additional flows have gone into tank 2 and 3. And then when the storm passes, return it to the interceptor where it will go to the treatment plant for full treatment. Now those are small storms and it happens. But in the cases where a moderate storm approaches and it's fairly certain that based on experience and other parameters, including looking at rainfall radar to make a determination, the treatment, the second goal kicks in where at a minimum the plant will provide treatment to all flows that enter the plant. Now that includes those that may go to the interceptor, but when the flows to the tanks are exceeded or expected to be exceeded, then the high rate treatment facility is turned on, and to begin to treat that flow and maintain storage capacity. And the third overall goal is to avoid overflows from the storage tank. And again, the challenge there is to make the call soon enough so that the high rate treatment plant can be turned on, and if flows exceed what the treatment plant can handle, then it may result in an overflow. But again, the first two goals are to minimize those overflows. Okay, with that explanation of the plant and how it operates, we evaluated what would be the sampling locations we want to identify to evaluate the performance. And we established four sampling locations. Number one being the influent to the plant, basically upstream of the influent pump station at the interceptor. Number two is the effluent from the tanks or the influent to the ballast flocculation process prior to screening. Number three is the ballast flocculation process effluent, which is that flow that comes out of the settling basins and flows towards the UV disinfection system. Number four is the final effluent or the UV disinfection effluent prior to discharge to the creek. Here, I'll quickly run through. Here's the manhole at the interceptor where we collected the influent samples. Down here, just prior to the screening, is sampling point number 2. Here is the sampling point number 3. Again, effluent from the settling basin. And 4, the final effluent or post-disinfection effluent prior to being discharged to the creek. As far as the sampling program, for each event, we conducted 3 rounds of sampling at 2-hour intervals at each sampling location. So basically, we took 3 rounds of samples every 2 hours to give us a 4-hour window of operation. For each event, we did traditional parameters, BOD, TSS, some COD, and those samples were a 1 4-hour composite made up of the 3 aliquots that we took during the 3 rounds of sampling. For each event and each location and each round, 1 grab sample for microbial analysis was also taken. And the more traditional or familiar microbial parameters, fecal coliform, E. coli, enterococcus, a couple viruses, the human adenovirus and the coliphage, and a few Cryptosporidium, Giardia, and aerobic endospores, parasitic indicators, or parasites in their spores. Here are some results from the analysis of the traditional or the conventional pollutants. And right up front, and what I have here is from left to right are the sampling locations, and from closest to nearest are the minimum measured values, the mean measured values, and the maximum measured values. This tells us a few things. First of all, you can see that if you look at the max to min, we have quite a range of variability here in CBOD removal. Across the plant, on an average, the plant's removing about 56% based on our sampling, 56% of the CBOD. As you can see, the influence samples vary greatly, with the minimum being below 50 and the maximum being over 350. What I find, and one thing I'd like to highlight is that even though the storage tanks are there to store water and return it to the interceptor or for treatment, the tanks by themselves do remove some BOD, and as you'll see in the next slide, the solids, they do provide some removal of solids and BOD in the process. For the TSS, overall, we saw a 66% reduction across, on average, from the influent to the effluent. again, there's variability, but not. We didn't see the variability as we did in the BOD, but still variability going from roughly 60 milligrams per liter, and I'm referring to the influent, and 180 milligrams per liter maximum. So generally speaking, that fairly dilute, as would be expected during wet weather. And again, we on average, it looks like the tanks removed about 15% of the solids. The upland solids also were pretty variable. As you can see in sampling locations 3 and 4, which should be fairly close, if not identical, because basically it's before and after UV disinfection. We see those ranges. So for the maximum solids coming out, it looks like we're around close to 80, maybe 70 milligrams per liter. And as you'll see in some of the microbial results, it appears to be that and as Kevin mentioned, when solids are allowed to when solids aren't removed, then UV disinfection especially isn't as effective. I want to share some of the results from the microbial analyses, and what we have here is for each of the events, the log reductions that we found across the high rate treatment system prior to UV disinfection. And I'm going to highlight, just for ease of viewing, and I know there's a lot of bars here and it gets a little confusing. These are the fecal coliform log reductions. You can see in about the first 4 or 5 events, at least through the high rate treatment facility, in terms of the reduction due to solids removal, we're somewhere around 1 log removal, and then past that we saw a much more variable performance, and talk a little bit about that later. But again, I think what you're seeing in the latter half of the events are some of those issues with controlling the solids. The full plant log reductions after UV, and again I'll highlight the fecal coliform. You see that again in the early events, we saw that the plant was in a few instances was approaching a 3 log reduction, which is I'd say in the low range of really what the plant would be shooting for. But again, very variable, and difficult, quite honestly, to point to any one factor. But because of the dynamic nature of the flows and quite honestly, the talent of the trickiness of operating this facility in terms of chemical addition, maintaining sand, and things of that nature, which I think is one area that, and I'll address that here in my conclusion, so I won't get into that right now. The last slide, I want to back up here. How can I back? No, I can. There it is. That way. Okay, here I am. Okay. One thing I want to highlight here, if you look at the first half of the events, you'll see the purple and brown, light tan bars. Those are the 2 coliphage samples or analysis results that, and I want to highlight this for 2 reasons. One, as Kevin mentioned, some of the experts from the experts workshop he held had talked about that it may be better to have a virus-related indicator organism, and currently the Office of Science and Technology is looking at the potential recommendation of using colophage as that indicator. And Kevin mentioned that UV disinfection typically does a better job on colophage disinfection than chemical, and you can see that here where we're getting several instances over a 4-log reduction of those colophage at this plant. So I wanted to, since Kevin raised it, and I do talk about this briefly in my conclusions, but I wanted to highlight that. And I would highly recommend, I've gone and looked, there's a very complete data and literature review that Office of Science and Technology has published as a draft document. I believe they're still accepting comments on that. So if you're interested in following up on how the use of these colophage as an indicator of fecal contamination and viral potential viral contamination, pathogenic viral contamination, then I would recommend you look at that information. Lastly, this is a average log of detectable organisms across the plant, and the top 2 lines are the E. coli and fecal coliform, again, more traditional or familiar indicators, and we basically saw on average that the plant got to about a 2-log reduction. Again, the variability in that affected that, but the plant did achieve close to 3 in some occasions. And again, the bottom 2 lines are the colophage, the green and the blue, and you can see here that those 2 results show that for those 2 organisms, or those 2 viruses, I should say, that the plant achieved close to a 3-log reduction on average. So in summary, again, I know this will be repeating, but I just want to reemphasize for conventional pollutants, both CBOD and solids, the average reductions through the system were 56 and 66% respectively for CBOD and TSS. And that the storage tanks did provide some measure of, if you will, primary-like removal, not to the levels of primary, but did remove 20 and 15% of the CBOD and TSS through settling. For the microbial indicators, the log reductions were highly variable, with the log reductions for fecal coliform ranging from 0.1 to 1.2 and 0 to 3.0 after flocculation, ballasted flocculation and UV treatment, respectively. As I stated just a second ago, the log reductions for colophage range from 0.5 to 4.1, and the overall average log reduction for fecal and colophage were 2 and 3, respectively. As far as the performance variability goes, the system showed that it could achieve high levels of microbial control, hitting 3 to 4 log reductions in several occasions. However, it appears that the variability, and this was very difficult because there weren't 1 or 2 things we could point to that said, oh, that's the reason for that. And so what I did was some additional investigation, and was fortunate enough to get the actual operator logbooks from those events. And it appears that what we may be seeing is a inconsistent removals due to O&M issues. And what I mean by that is throughout those logs, and not in every occasion, and not the same notations in terms of equipment issues, but there were, and especially I noted that the issues were around the chemical feed operations and equipment, and the sand replacement. I think, and it's ongoing now, ongoing improvements to both the control and monitoring systems, which has just started at the facility. They're upgrading the SCADA system, and prior to that, an intensive RCM, which stands for Reliability Centered Maintenance Evaluation, was done at the plant, where plant operators, maintenance folks from mechanical, electrical, and instrument maintenance folks were on the team, engineering folks at MSD, to identify those critical maintenance needs, identify those critical assets in the plant, and really refocus and improve reliability and performance through a almost an asset management based maintenance focus, where high priority maintenance to those critical items will be and is being adopted. So I have every confidence that the plant will be and is improving its operations to be more reliable and more steady performance. And so I wish I could say it was this or that, but it's such a complicated process, quite honestly, and it relies on critical equipment. And the last thing last point I'll make, many times these plants sit weeks and months, and then are needed immediately when it rains, and oftentimes equipment that's turned off and on and off and on can require more maintenance and more oversight. And like I said, I think this RCM process really is focused on MSD on this, and I'm sure the plant will operate much better in the future. And that's all I have, and I'd be happy to take the questions.
Okay, great. Thank you, Dan, and thank you, Kevin. So now it's 3 o'clock, so hopefully you can stand for a few questions. And up on the screen are the next talks in case you have to leave. The next one's on treatability databases, cost models, and other tools for water systems, including chloramination calculations for drinking water. So I hope you can attend that. Also, the CEU credits will go out based on this one. Last month, we're a little bit behind, so you probably haven't seen the certificate yet, but you will very shortly. So I wanted to let you know, just in case you had to leave. And if you have to leave, thank you very much for attending our webinar. So we have a series of questions, and I'll start with Kevin. So Kevin, your first question is, please describe more what was done with the chemically enhanced primary treatment. Alum addition, polymer addition, coagulant control tools like streaming current detectors?
Thanks. That's a very good question. Unfortunately, I don't have all the information here in front of me. I know that for the facilities we looked at, there was polymer addition and alum addition. Typically, when a facility takes a look at trying to increase the treatment efficiency, they'll also get into the flow patterns and make some modifications, physical modifications too. And we'll make sure that a more complete write-up is in the compendium when we have a draft available for it. But very good question.
Okay, thank you, Kevin. Here's another one. There are cities that are proposing chlorine disinfection of untreated CSOs for their long-term control plans. How does EPA view this? Okay, so under the Clean Water Act, the disinfection requirements are water quality-based requirement, which in essence means that it's a site-specific determination. But having said that, we would probably have
I think that would be a difficult situation for EPA to agree to in a long-term setting. The CSO policy calls for at least primary treatment prior to disinfection. As Dan and I have talked about, the solids in the effluent are going to impact your disinfection efficiency. So that's a big factor that we would be looking at. We recognize that some facilities, while they're implementing their long-term control plan, may be disinfecting untreated CSOs, but we typically would be much more comfortable if that was an interim thing until some sort of solid reduction occurred.
Okay, great, Kevin. And one more. What are the ranges of CSO, SSO flows that ballasted water flocculation has been used? Can they be used for CSO, SSO flows of 50 million gallons a day or more?
Yeah, this is Kevin. The one facility that I reported on, the Toledo, Ohio facility, which used the Densideg ballasted flock system, was 185 MGD facility, and it's actually 6 units at the facility. So what happens is that you can put multiple units at a facility. They can be used out in the collection system, although that's creates some specific problems in terms of operating the systems. Most folks are more comfortable with getting the flows down to the treatment plant or in and around that area so that they can send the operators out for them. The Bremerton, Washington facility is a excuse me, a CSO facility. And it's an active flow system. The Blue Plains facility, which is the treatment plant here in Washington, D.C., is in the process of installing a fairly large active flow system, and I'm sure it's above the 50 MGD. I don't have the specifics in front of me, but they're going to be treating their bypasses with an active flow system once their tunnel system comes online, which will be in a couple of years.
All right. Thank you, Kevin. Okay, this one's for you, Dan. How do you determine the rate of blending once a storm has passed? Do you aerate, and also do you aerate the holding tanks? So when you're doing that trade-off.
Right. Let me ask the second part first. No, those tanks are not aerated, mainly because it's within 24 hours or so of the storm that those tanks would be emptied. As far as the first half of that question, the rate of blending, I'm assuming you're talking about when the flows return to the interceptor. That's a function of the capacity of that interceptor as it decreases, as the flow decreases. So it's a variable and based on that. So yeah.
Okay, great. And here's another one. Can you elaborate on the purpose of adding sand to the HRT? What benefit does it bring?
Yeah, the sand is actually in the term ballasted flocculation. The sand provides the ballast. In other words, it's a very fine sand, fine enough that when it goes through the flash mixer, it's actually it's almost completely suspended in the water, in the flow. The goal for the plant is to have around 2 grams of sand per liter in the tanks. And then when the coagulant and the polymer are added in succession, the flock that's created is, because the sand is there, it pulls in that sand. As the flock gets bigger, that piece of sand, this conglomeration of sand and waste solids are then heavier and they settle much more quickly in the facility. And so for a high rate treatment where the flows are moving through there quickly, you want to really get that flock created, and it's heavy, and it settles out quickly. And so that's the reason for the sand, is to help settle that solid out when the flock is created.
Okay. And here's another question. In your study, were different doses and types of different coagulants tested?
No. We did not vary anything. We were there when they were operating the plant. So what they've used since the plant began at the rates required based on the flow into the system was what. So the rates may have changed because the flows were different, but the chemicals themselves did not change.
Okay, great. And here's a question I'll throw out to Kevin and Dan, depending on who wants to take it, or both. We had a couple questions about how much these facilities cost and what is the cost per unit volume for these facilities.
For this facility, I don't have I could get that, but if the person who asked the question wants to email me, murray.dan@epa.gov, I can get that information for you, both operational costs and design costs and construction costs for the plant here in Cincinnati. I don't know in general, Kevin, are you aware of any cost per gallon or something like that for operations of these systems?
Dan, I don't have it off the top of my head. I mean, the various vendors make that information fairly readily available.
Okay. Here's another question for Dan. Are there any high-rate clarification processes that is able to start up without operator intervention, automated systems?
Yes. Yes. This plant can be remotely operated from the main treatment plant, because things such as maintaining the levels of coagulants and or at least checking those to make sure they're adequate. Probably the most critical piece for this technology is the sand, because you really have to stay on top of that. You have to they use a when the sludge sand mixture goes into the hydrocyclone and is dropped into the flash mixer, the operators really have to reach in and grab a sample, and they use a settleometer to determine the quantity of sand in that sample. And because sand is such a critical part of the process, they're continually adding time to time additional sand. So you can start the plant remotely, but there are functions at the plant that require an operator to be there.
Okay, thanks, Dan. This is for Kevin. In Chicago, the water quality standards for bacteria were just put in place for their waterways. How do we encourage CSO treatment rather than the anticipated MWRD that they will apply for a variance?
I think the important thing to keep in mind is that for most cities, their CSO control effort is a work in progress. Typically, there's a long-term control plan that sort of guides the process for doing that. Variances are typically are temporary in nature, and they're typically issued to allow the facility to complete their work on in the various projects that will bring it under control so that they can meet water quality standards. So the water quality standards going to remain, even if there's a temporary variance. It's hopefully a matter of time before the facility is able to meet the standard.
Okay, thank you, Kevin. Let's see. So Dan, why did the TSS increase between sampling events between locations 3 and 4? And I think it was on here.
Yeah.
This plot there, a little bump up after.
Yeah, yeah. Once I saw that question in the queue, and now that's one analysis. That's a maximum number on both of those. So those samples were taken a little bit, apart from each other. I would say, and if you look at the, I would say that's probably well within the range of variability of both the analysis and the sampling method. I don't think that shows that anything happened there other than there's some variability in that range. That's probably less than 3 or 4 milligrams per liter.
Okay, and a very similar question. I think a little later you showed a negative log removal for fecal coliforms after UV. A little blip on one of them. And the question was, how can that be possible?
Well, it'd be possible when the sample taken after UV was higher than the sample before. I mean, we did have, again, that's probably, there were, so, there's very much more variability in microbial analyses, and probably, again, that's in an event where they were having some issues, so probably not unexpected.
Okay, great. And another question about what is the ballast return time in the system?
Yeah, once I mentioned that for about 15 minutes, and I think it's at about 3 mgd, is the startup flow rate. And what happens is the plant is run for 15 minutes, and once things are up to where the operators feel they need to be, then the plant is put up to the operational flows. Once that happens and that sludge starts coming out of the settling basin, it's going directly to the hydrocyclones for separation. So and the plant isn't that big area-wise, so it's continual and throughout the process. So there really isn't it isn't like they draw some off and then wait. It's a continual return, because again, that sand needs to be returned to make up as that water's coming in into the high flash or the high-speed mixing tank.
Okay, great. Well, I think that exhausts our questions for the day in our queue. And I'd like to thank our speakers, Daniel Murray and Kevin Weiss. And thank you to the audience for attending our Small Systems webinar. Again, in November 24th, there'll be a webinar on treatability databases, cost models, and other tools for water systems. And then this one will be specifically on drinking water systems. So I hope you'll be able to attend next month's webinar. Thank you again for attending this one, and I hope to see you next week. Thank you. Next month, I'm sorry.